So chapter 3, 1 and 3. That was the recorded lecture thing. Didn't do that. Anybody do that? Nobody did that? 1 and 3, chapter 3.
But I did it wrong, I think.
Okay, that's all good. So let's carry that over. We'll put it on today as something to do. How about chapter 2, 15, 16, 17? I know we did that one, right? Did I grade that one?
No.
Okay, you have that one?
Yeah.
All right.
Right.
Here's this coming back. Let me give you the Evan. Small paper about that.
Doesn't exist anymore.
I saw that. On. Okay, yeah, I don't. Okay.
Just put your request through the whole.
Oh. Yeah. What's there?
The first two assignments, so.
Yeah. Oh, good. All right, so let's talk about, you have in your hand 15, 16, 17, chapter 2. If you did it, right? Chapter 2. I don't know if these will be the same or not, but we can look. Because this is a different version of the book.
That looks great.
15 looks right?
Yeah.
It's a log.
Yep.
Just turn that in. We didn't turn 12.
12, 18, 20.
12, 18, and 20.
Yeah, chapter 2.
Did you upload that one?
No.
Oh,
We
maybe
didn't.
that was it. Oh, I did.
I think,
Were we supposed to upload it?
12, 18.
no,
I didn't.
I didn't put it up.
Wait, did we not turn it in then?
That's the one. You should have it.
Oh, I do have. Yeah, but I
So-
didn't grade it.
So.
So that needs to come in. Well, that makes sense because I assigned it on Friday. So 12, 18, and 20, 15, 16, 17. If you have them done. If you don't, get them done, turn them in. All right. Questions? Is there questions? 15. What's it want to know? It wants to know, we got a cable pulling on a log, determine the magnitude of the force tending to lift the log and the magnitude of the force tending to slide the log, right? So that's why force up.
That's 18. I don't know why. It's 15 for you.
It's different book. So they just reorged everything. So what's 15 look like?
15 is.
Is this probably in
I
here?
think that's two
It's
triangle.
the. Yeah, it's a huge triangle.
No.
Number 12.
This one?
Yeah.
All right. Oh, I remember talking about this one in class. Parallel and incline. So that's where you have to rotate the axis. Yeah. You have questions on that? You want to do that? This is actually, did you know how to deal with the 3, 4? Yeah, it's just giving you the rise and run of a triangle. So you can just finish the triangle out, find an angle. So where that says 30 degrees, this is going to be a different angle here. You want me to do it or are you good with it? Silence. Nick's good with it.
Really?
All right, so then what was the next one?
That one.
This one, the truck?
Yeah.
Same kind of problem where I think they're gonna say vertical and horizontal components. No, 13. Determine the vertical and horizontal components of the 1,000-pound force that acts on the tip of the boom shown. So again, just want the two components, right? They want X, which is gonna be negative, and Y, which is gonna be negative. So remember, either put the negative sign on those forces or put the little vector next to it pointing down and pointing left, right, for the X force. Either one's fine. If you put negative, I'm gonna assume you mean negative direction. If you don't put negative, I'm gonna assume you mean positive direction unless I see a vector going some other direction. Either way is fine. Questions on this one? Or are we good? So if it showed up on a quiz, you'd be happy, like, no problem. Gina's like, oh, I'm not that happy with it. I don't know about that. All right, let's just look at this one. I'll talk you through it. So some boom, right? Off the truck. And then was the 1,000 pounds
It was perpendicular.
is a perpendicular, yeah, perpendicular with the boom, and it's at 40 degrees. All right. So this is 40 degrees. Yeah. And then this is perpendicular at 1,000 pounds. Yeah, and they say find the horizontal and vertical. So this one and this one, so this will give me the opportunity to emphasize that those two components come from this point, and I don't know if they labeled that point. I'll label it A, but the two components do come from the point, right? Because that's where the original force is. But to make the triangle, it's what you do is you move this one over to here, right? And this becomes the vertical, this becomes the horizontal. You can call it X, you can call it Y, or H and V. Either one, you're gonna find it both ways. Just becomes a right triangle trig problem. The thing you have to do is figure out, well, if this is 40 here, right? How can we transfer it up to here somehow? Or can we transfer it up to here somehow? So that's the game, right? Is to figure out, well, give me an interior angle here. So how'd you do that? One.
I dropped in like downwards. Like
There?
Right there.
Yeah.
So, and I put out an imaginary line 40 degrees. Farther out.
Wait, here?
Where it's horizontal. To the left. To the left.
Okay, I'm liking
So
all
there's
this.
a right angle right there.
Yep. So then you got this,
50. 50 right
Yep.
there.
and then this is 90, right? So this is 40. Yeah, I like that. I don't know, honestly. Oh, it's the boom problem. So it's this one. Okay. The truck problem. Yeah, I don't know what number it is in your book. It's different in my book. My book should be here soon, so that's good. So that works. So then we know 40 and we know what here. Yeah, 50. Good. So however you pick that out of there, that's really the problem, right? Is to try and figure out an interior angle inside of the triangle. Now I have this triangle, the two green sides and the hypotenuse. So a lot of times I'll draw that off to the side, just kind of for clarity, knowing that this is 1,000 pounds, this is 50 degrees, and I can go for the vertical and the horizontal effect. These two effects are the same as the original 1,000 pounds. So that's a super important concept. The components give you the exact same effect as the original 1,000 pounds. There's not three vectors at that point, right? There's really one vector, it's the 1,000 pounds. Everyone agree with that? But we can take the 1,000 pounds and get rid of it and put the components in, and the effect is exactly the same. Does that make sense? You just see it differently, right? We see X and Y instead of the 1,000 coming off at some weird angle, right? We need X and Y effect typically to do analysis and to definitely do design. So that's why we're spending so much time trying to figure out this horizontal vertical effect of a force. All right, so what do we get? Horizontal is What? Anybody calculate that number? If I wrote it out, it would be cosine 50 is horizontal over 1,000 pounds. And horizontal is going to be equal to cosine 50 times 1,000. Exactly. 642. 0.79 pounds, and it's pointing that way. Yeah. Very good. And then this would be sine 50, right? 50 sine 1,000 times vertical is going to be 766.04 pounds. Pointing down. All right, gonna go down effect. Cool. All right, what else? What was the other one? The log one was 18. In this homework set?
The last.
It was.
Yeah.
Same kind of problem. We just now need vertical, horizontal. Easier problem because we were given the 42. So the place to make that triangle is down here for horizontal and then up for vertical. All right, what else? What else did you do? 15, 16, 17, 12, 18, 20. Any questions on any of those other problems? Try to find them, but you'd have to tell me when you see them. I think you said one of them was this one, right?
Yeah.
Yeah. Let's review one of these. So this one. Right? The 3/4 is just giving you the rise and run of a slope. So you should be able to get this angle theta by saying what? Tangent theta equals 3/4, opposite over adjacent. And that's what I do right away, just get it in decimal degrees so you have an angle to work with. So that's going to be the inverse tangent of 3/4. $36, 8,698.9. You're going to want to carry that out a ways if you're going to use it to calculate with. And what this wanted to know was the components, horizontal and vertical, parallel to the slope and perpendicular to the slope. So that means essentially rotate your axis. So because that's what they want, is they want that effect. They want parallel to it, it's going to be down, and perpendicular to it, it's going to be into, because those components add together tip to tail to make the original force. So starting here, go down because it has down effect, and then tip to tail, it has left effect. So that's what they want. This would be the parallel. This would be perpendicular. what we have to figure out is like, again, we got the angle, but how does it transfer up to the triangle that we just drew? So. Again, however you want to do that, or however you see it. The way I see it is this is vertical. And if this surface rotates through theta from here to here to get to horizontal, then this would also rotate with it, the same kind of angular degree. So to transfer it up, normally it's that angle and this angle. They're going to be the same. They have to be, right? So as this thing rotates down, right, the perpendicular would rotate the same amount of angular change. So however you want to see it, or however you can see it, or if you need to build some triangles, because you could build triangles too, right? You could put a horizontal up here, and then that angle is the same as that angle, correct? And this to this is 90, so that gives you this interior angle. So that's another way to do it. So this horizontal, this and this are the same, so that's theta. And horizontal and vertical, that's 90, so you can go 90 minus theta to get this inside angle. Again, however your mind is going to work through it to transfer that angle up there. You see that? Well, yeah.
Not really, can you draw it out?
Yeah, so horizontal and horizontal, correct? You okay with that? And then one slope going through both of them. So this angle and this angle are the same. It's theta. And then from here to vertical is 90. So this whole angle is 90. And I know theta is this lower part, but I don't know this interior part. So if I drew it bigger, that's this one. That's this one. That's this one. So here's the horizontal, here's theta. Right? And from here to here is 90. Here. So this is going to be 90 minus theta. Theta is 36, so we have 90 minus 5313. Right in there. 53.13 degrees. Right? Interior, we have now an interior angle. This is 150. This is PER perpendicular. This is parallel PAR. I should be able to solve that. Right? It's a right triangle. A lot of these problems, that's the hardest part, is like digging out the internal angle. Draw the triangle off to the side. That's going to help because, it gets cluttered. So then if I want to know the perpendicular force, that's opposite. That's going to be sine of the 5313 equals opposite. I'll call it PER. That's the perpendicular force over the hypotenuse 150. Equals 150 times the sine 5313. 120. So 120 pounds of that 150 is going into the ground or into the slope. The amount going parallel, this one, is going to be cosine. AR parallel over 150. So the parallel equals 150 and lost my angle. So I'm going to have a rounded angle. But that's all right for that. 6. Anyone else get 6? Do it again. 53.13 cosine seems small, 150 times 90. Definitely not 6. 0.00. That's very important. You get that?
You got the 90.
These are what we call slope problems. And it's important because if we want to know anything about sliding or any kind of a system that's on a slope that could move down the hill, a house built on a slope could move down the hill. If there's not available friction in the soil, if the soil gets super wet, gets slippery, houses slide off of cliffs all the time in certain locations. So the amount of down the slope force is something we're very interested in often. So of the 150, 90 pounds of it is going down the slope. So if you want to think about ice and like your feet, right? So here's my boot on an icy slope, and I weigh 150, I wish. 90 of that is going down the slope. So between the boot and the ice, if there's not enough friction to hold 90 pounds, whew, right? You slide. Your feet go out from under you and you're down. So yeah, these are common things that we calculate. If you put chains on your boots, those boot chain things, those things work. Just saying. I thought they were always goofy, but they work. That's going to increase your frictional capability a lot and probably carry that 90. So, all right. Good. Any other questions on the homework that you have in front of you? Now's the time. Could show up on a quiz. Threatening that. Any of these creatures? I like these real ones. These
Not on the 1 and 3.
Hmm?
Not on the 1 and
No, we can do chapter 1 and 3 because if you haven't done it, you're gonna start on it. So the one that I put up, let's see. Yeah. 1 and 3. It was due Monday, but now it's gonna be due like Friday. Is out of chapter 3, and chapter 3 is resultants. So kind of what we've been doing, honestly, but they can get a little more complicated depending on how we have to calculate them. So the first part of chapter 3 is this resultant of 2 concurrent forces. So in that lecture that I put up and recorded, I talk about concurrent forces and non-concurrent forces. So we don't have a lot of force system terminology, but this is one they use over and over. Concurrent force system is a force system that comes out of the same point. Focus. There we go. Right? Comes out of the same point, obviously concurrent, going through the same point. But there's others that are less obvious. Here's a beam. And here's a force. And here's a force. Would you think that's concurrent? Doesn't look concurrent, right? But we can move a force anywhere along its line of action. Anywhere along its line of action, it's called the principle of transmissibility. We can move a force. The effect is the same for statics. And I'm gonna make that clear, just for statics. Strength of materials, the effect is different because we're studying different things. But in this class, what this is saying is, if you have a car, I'll put it in terms that some of us can understand, right? That's broke down, and we need to push it. Right? So we can push with maybe 100 pounds. Most people leaning into something could push with 100 pounds. And we get the car to move nice and flat. It's got good bearings, rolls right along, okay? So the principle of transmissibility says, hey, if you hook a rope onto it and you pull with 100 pounds, what's the effect? It's exactly the same. It's the exact same effect. So statics, that's all statics cares about is the effect of forces. So that's moving the force anywhere along its line of action. The height would have to be the same, the force would have to be the same, and it would have to be along the line of action of the vector. Okay? Just in this class, because in strength of materials, we understand and do analysis of the materials. So it matters where the force is applied in strength of materials. Like if I'm gonna understand like, whoa, how does this 100 pounds affect the back window, right? Because maybe I'm pushing on the back window. Well, that's very specific to the back window. We can't just say, oh, this is not on the back window, it's on the front of the car. Well, it's not if you're pushing on the back, right? So strength of materials is trying to understand the response to these forces. Statics is not, doesn't care about that. Like, I don't care about the response to these forces. I just care about how to understand the forces. Yeah.
Is that considered statics? Statics?
Yeah, it does. It's statics because it's what we'll call impending motion. So we'll calculate how much it would take to move it. And then compare it to the 100 pounds and say, oh, that moved or that didn't move. But that's all we can do. Yeah. All right. So these are a little bit tricky because they can act like concurrent forces. Now, if I add another force here, is there any way that all three of these intersect at one point? No, this is a non-concurrent force system now. Okay, so concurrent meaning they go through the same point. Non-concurrent meaning all those lines of actions do not intersect at one point. So that's the terminology that they're playing with in the book. The other thing they talk about is planar. Coplanar means all the vectors are in the same plane. It's not a three-dimensional problem. Okay, so for example, this is a beam. It does have width, but we're just going to act like it's no width or a single unit width. Like if it's 1 foot, then the one drops out of everything as you calculate it. Okay, so it's a per unit of depth that we do our calculations. So it just simplifies things in the beginning. And then we do some three-dimensional stuff in the end. So when they say coplanar, that just means that all of these lie in the same point. All these lie in the same point. It's not a three-dimensional problem. All right. Good. Good, good. So the first part of this chapter is resultants of two concurrent forces. There are two methods to do it. There's the triangulation method or the parallelogram law, which means take this vector, move it over here, take this vector, move it up here, and it creates the location of the resultant. And by doing that, you can build triangles and solve the triangles for the resultant. R. This is R, the single effect from the two vectors. So when the vectors are not X and Y, this is one method of doing it. They call it the parallelogram method. And there are reasons to do it this way. If you're missing information about some of these vectors, like maybe you have the angular position and you have the force magnitude of one of them, but you don't have the other, then you can't really do components. So you have to have some other method. Triangulation is this method. So it's building this parallelogram, only two, right? Two forces. So you have to start to kind of categorize your strategies. Hey, I have a 2-force system. I can do this with it. Uh-oh, there's 3 forces now. I can't do this with it, right? You can't build a triangle out of 3 forces and have a result, because that'd be the 4th factor. All right. So resultants, let's just clear that up. They are the single force that replaces P1 and P2. So sometimes we want to know, well, what's the total You know, we have a telephone pole buried in the ground, right? And wire coming off, guy wire coming off, and another wire coming off. This one's kind of swoopy, but we have this. That's great. We have all this going on, but I need to know what the pole feels, right? I don't know what this pole feels. I know that it feels a lot, going in a lot of different directions, right? So the resultant is like the single force. What's it feeling? At what angle? So in order to design this thing, to figure out how strong it needs to be, I need to know, if this is 100 and this is 150 and this is 100 and this is, who knows? I can calculate that because we're going to put this thing in equilibrium. Once I get this, then I can find the resultant of everything that's going on. So that's what a resultant is. It's important. If we have a ground anchor, comes up to something and it's got a few forces coming off it like this, I need to know the resultant, what it feels, right? All three forces, that's great, but I need to know the single effect. Then I can say if that's good or not. But if this is 400, this is 500, and this is 100, okay, I still need to know the single effect before I can do any analysis on that. The resultant is that single effect. All right. Cool. Very cool. So I think the second part, they do maybe components. Oh, 3 or more. So if you have three or more forces, right? Here's a whole bunch like the one I just drew. Like, what's the resultant? You're not going to build a parallelogram, right? That's just it. You could take these two, build a parallelogram, find the resultant of those two, and then add your resultant to that one, build a parallelogram, find the resultant of those, and then add that one to the resultant of the, yeah, it's like, no, we don't want to do that. I mean, you could do it that way. This is components. This is going and saying, okay, what is the X effect of the 12? Going that way. What's the Y effect of the 12? It's going that way. How big are those? Right? What we did. That's what we just got done doing. It's finding the X and Y of this, finding the X and Y of this, finding the X and Y of this, and then adding them all up with positive vectors going this way, and negative vectors going this way, and this way, right? Down and left, this negative. So 3 or more components. 2 components works. I'm a big component guy. Or the parallelogram.
You draw a picture how you'll do
Yeah.
that, you just have,
Yeah, let's do some practice ones. I think that's what you're saying. Like, hey, can we do one of these? All right, so let's do one of these together. Meaning you get to like calculate it too, and I'm just gonna make it up. I like real problems, so we'll do the whole helical pile in the ground to an eye bolt with 400 pounds here and 600 pounds at 40 degrees. All right, and just for fun, we'll do it by the parallelogram law and also by the components. So we'll do it 2 different ways just to check our work. I'll give you a second to write it up. And this would be find R. What's R stand for? Resultant, yep. The single force that can replace the force system.
something like this is because it's a real world scenario, so it probably wouldn't matter, but those arrows are supposed to represent the amount of weight that's pulling.
Yeah,
So that's for a,
No, I mean, it's good practice to draw those vectors appropriately, not the way I did. I think is what you're saying. So the 600 should be longer than the 400. Right? Is that what you're saying?
right, but
Yeah.
it's a specific diagram that does that, right? In real world, it wouldn't.
Yeah,
necessarily-
like, no, if I was gonna write this up, I try to do that. That's good practice, but you see it all the time. Just vector and then put some magnitudes on there.
Yeah, okay.
But if you do it this way, right, and then you use the parallelogram law to draw the resultant, which means just stay parallel here and stay parallel here, I'm gonna say that's horizontal, right? Then it does give you the magnitude of the resultant. Like you could do this in AutoCAD and get the solution. That is R. Is it greater than 600 or less than 600? Based on the graphic. It's longer than 600. So I'm guessing R is what? 800, something like that? Just graphically looking at it. It's big, right? So that's a number that we're looking for. And we drew the 600 longer than the 400, and I'm approximately 40 degrees. All that's approximate, right? You could do an AutoCAD and make it perfect and get the right answer. So that's always fun to do. So this is the parallelogram law. We have to dig out some angles. We have to figure out like, oh, I need something here to help me figure this out. I know that this is 400. I know this is 600. I know that angle is the same as that angle. Right? So this angle here is 40 degrees. So now I'm looking at R 400, 600. And this angle is what? If this is 40, yeah, then this is 120? No, 140. Right, so I had to dig out some angles. But now I have side angle side. And how do we solve those? What law? Sine law or cosine law? Cosine law. Because we don't have an angle and an opposite side. If you don't have an angle and an opposite side, then you can't use the sine law. It's got to be the cosine law. That's going to be r squared equals 400 squared plus 600 squared minus 2. 400, 600 cosine 140. Just happen to have that one in my memory banks. I get 942. Sweet. Is that everything that we need? Yeah, so we do. We need to know, because this vector is like this, and I need to know that. So that's this. So we have the position, it's here at the eyeball, maybe that's point A, so that's point A. So this is the resultant at A. So we have the point of application, got the magnitude, I have the sense, but I don't have the direction.
Sign.
Right.
Yeah, sign law for sure. Because now we know 140 and R. Don't want to round it, so I would write it probably 942.17903 over the sine of 140. That's going to be equal to 600 over the sine of A. Right, opposite side and angle. So that would give me an angle A of. Oops. Low battery, that's sketchy. So how long I can go on low battery. What'd you get? 24.16 degrees. 24.16 degrees. Boom. So that gives me the total load. Right? So now I know more information about my poor little helical pile that's in the ground. It's feeling 942 from this 600 and 400, right? So the other way to do it is just to collect the effects. So that's parallelogram law, building a right triangle or a non-right triangle. I don't know if I can get any more of this in, maybe. So the other way to do it is the components. Just figure out all the X effect and add them together. Figure out all the Y effect and add them together. From that, you have X and Y, the components of this R, the resultant, right? So what is the X effect of the 400? Yep. So F X of the 400 is 400 pounds. Which way does it point? Positive or that direction? Right, so I'm just collecting the X effects first. So what is the X effect of the 600? Yeah, so that means I need the 600. Right, and the 40 degrees. And I need to know the X effect of it. That's here. Right? How do I get that? Cosine. Because this is just a right triangle, right? So, cosine of 40 is going to give me this X effect. So cosine 40 equals, I'll call it Fx of the 600 over 600. So Fx of the 600. It's notation is important when you're doing components. You have to keep track of this stuff. So. $459. 0.6266. Which way does it point? To the right, which is positive. So it's a plus, and it's going this way. So there's the two x of x of the two original forces, 600 and 400, right? These two. So, like, if you were gonna do this problem, you'd probably redraw the problem. 600, 400. And you would not do the whole parallelogram thing, because you're not doing that technique, you're doing complements, right? So then I usually like do something like this, like, oh, here's the x and y of the 600, and then the 400 is pretty straightforward. So we just found that creature, added to that one to get what we call Rx, the x effect of the resultant. So you're adding together or you're summating all of the Fx forces, add them up. If there's 10 vectors, you find all the x components of all 10 and you add them up. Negative directed forces are negative, positive directed forces are positive. So in our case, we've got 400 and 459, right? 859.62667. That's the x effect. Make sense? And the y effect. So we do the whole thing again, just looking at the y's. What's the y component of the 400? 0. It has one. It's equal to 0. So we just need the y effect of the 600. That's this creature right here. Yeah. And that's going to be sine 40 times 600 equals Fy of the 600. $358. $385. Dyslexia going on there. 385. 67257. Sorry about that. 385. Somebody else get that number? Okay, good. Which way does it go? Up. Definitely up. So it's positive. Up. So there we go. There's our two effects, our y effect and our x effect of the resultant. All right. So that means we've got 859 and 385. I'm not going to write all the decimal points in, but that's the two effects. And then that creates R. And it should be the same R as we got here. And it's just Pythagorean theorem, isn't it? To get R, square, square, add them together, square root. Because this thing's really here. We know the two sides and we want R. So let's check it. You want all the you need no rounding. So you want all these numbers. I have them both stored. So I'll square that one, square that one, add them together, and then square root. That didn't work. Oh. I get the exact same number. Yeah, did you all get the same number? 942.179, which is 1/8 pounds. And then guess what this angle is? Should be 24, right? So if I did the inverse tangent of the 385 and the 859, I'm gonna get the same angle. Two different techniques, same solution,
First,
good times. You like the first one better? Wow. First one you can do if you have two vectors. If you have three or more, complex. Unless you want to do parallelogram, 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 which you can do, that does work. So either way, most of the time, if the problem tells you to do it a certain way, then do it. It's good practice, right? Obviously, in real life, you get to do it however you want, whatever works best for you.
so you did a split with research on.
To get 942, yep. Yeah, because we know the two sides of a right triangle, so it's just pythagorean there. Yep. Good. Questions? All right, let's turn all the homework in. Let's take a break. 10 minutes, solid 10-minute break. I'll start up at 5 after 9-ish. We'll do a little more and then we'll cut it off. Any homework you have, turn it in. Any homework you don't have, get it done and submit it not late.
I have all my homework done, but I just didn't bring nothing.
So one of your problems is gonna have you calculate this thing called a moment. But let's talk about why we need them. So if we have a force on an object, so this is a box. Can you see that? Yeah. Right? And we have some force applied to it. That force is trying to do three things to that box. Let's see if we can name all three. What do you think that force is trying to do to the box? More specific.
Sideways to the right.
Pull it to the right. It's trying to slide the box. Agreed? So the box could slide. What else could the box do? What if the force was 400 pounds and the box weighed 1 pound? Lift it. Yeah, it's trying to lift it. So that's just your X and Y effect, right? It's trying to slide it and it's trying to lift it. So those are called translations. It's trying to translate it in the X, move it, and it's trying to move it in the Y. Agreed? That's called translation. Moving in the X, moving in the Y. What else is it trying to do? Let's say the box weighed 500 pounds and the force was 500 pounds and this point stuck. It's just sticky. It's a box on carpet. Trying to pull it, definitely doesn't slide, but it could rotate. It could tip, right? So this force is trying to translate and also about that point, rotate. Those are your standard three effects that a force has on something. Translation, X and Y, and rotation. This rotation effect we call a moment. All forces have rotational effect. Sometimes the rotational effect is equal to 0. It's kind of like all forces have X and Y effect, but sometimes X is 0, sometimes Y is 0, right?
Is there like a Greek symbol or something used for a moment?
No, just M, fortunately. Yeah, yep. So we want to capture this effect of forces. We need to understand that rotational effect. The equation for moment is M equals force times distance. Pretty easy equation, right? But in order for a moment to occur, there must be a distance between the line of action of a force and the point that you want to take the moment about. So moments are very specific about a spot. They're not just like anywhere. They're at point A, or they're at point B, or they're at point C, okay? Moments are very specific about a spot. So the book shows something like that as the example of a very standard moment. If you've worked on a car or anything with a nut and a bolt and a wrench, it's also a torque. It's the same damn thing. But engineers got to be different, so we call it moments. Until we get into topics in the future, like torsional stress, which we use torque. So you're gonna have to get comfortable going back and forth between torque and moment. It's the same thing, okay? It's the rotational effect. If you have a wrench on a bolt, right, and you put a load here, we're trying to do what to the bolt? We're trying to twist it. And that force is a distance away from the bolt. Agreed? If we were to take the same system and do this, how well are we going to spin that bolt? Not very well. It's like trying to open a door by taking your finger and pushing on the hinge. Good luck with that, right? The door's not going to open. Agreed? That's because you're putting the force straight at the rotation point. So when the force goes through the point, it creates no moment. No moment. When the force does not go through the point, it creates moment. So if this is 100 pounds and this is 6 inches, we use this equation to calculate it. M equals force, 100 pounds, distance, and I put a little perpendicular there because the distance has to be perpendicular to the force. So my force here is a nice vertical force. My wrench is horizontal. This is gone. All right, this is the one I'm doing, and that is perpendicular to the distance. So that means I can use that 6 inches directly. Since the moment is very specific about a point, you have to label your M with a point. M sub A, moment about A. Right? If they don't give you a point, then you label the point. But the moment can't just be M. It's got to be about a point on the diagram that you've drawn. So moment about A, 100 times 6, what's my answer? 600, what's the unit? Inch pounds. Well, it flows off my mouth a little easier than pound inch. Inch pound is what I call it. You can call it either one, right? Inch pounds. All right. Moments have, just like vectors, they have characteristics that we need. We need point of application. What point is my moment at? A. We need magnitude, 600 inch pounds, and we need rotation. We've got to have rotation. So what kind of rotation is this force making about point A? Just like that, right? It's trying to spin it around. So I use that symbol. The sign convention for a moment is the same as AutoCAD. Counterclockwise is positive, clockwise is negative. This is clockwise, you can put the negative here, you can put the negative here, however you want to do it. This also, that symbol represents clockwise, it's gonna work for me also. But that's a negative rotating moment. And the negative is only a directional thing, just like vectors, the negative is only giving us direction, right? We don't really have a negative force, that's a vacuum, yeah. We don't really have a negative moment, huh?
Either make it negative or. put some-
Yeah, if it's negative, then I'm gonna assume you meant a negative rotating moment, right? Or the symbol, or both. Like, it's so easy to miss it. Like, when you're adding these moments up, you gotta keep your positive and negatives going correctly, right? But that's it. That's all a moment is this rotational effect. Why do we need it? Because in non-concurrent systems, systems that look like this, like your homework, they're not concurrent. The only way to solve these is by collecting the translational effect up and down, right and left, and the rotational effect. You have to collect all of it to understand what the resultant effect is. Because these forces, if I'm here at A, they're all trying to rotate this, even though it's locked down with its supports, they're trying to rotate the object. Okay, and we need to collect that effect. We have to. So at A, this one's trying to rotate like this. Yeah, everyone's spinning all different directions, right? At B, everything reverses. So it's very dependent on where you choose. And in the end, we get to choose whoever we want, but we have to choose a spot and focus on that spot and then collect all the effects. Right now, we're just going to practice calculating. And they're going to give you some easy ones, right? Anything vertical, you just use these distances to calculate the moment. Super simple. Parallel systems are the simplest and honestly the most common in the beginning, right? Because gravity's doing what to stuff? Pulling it straight down. So if you have a bridge and you load it with semi-trucks, all those semi-trucks are doing straight down. And you have a horizontal bridge, pretty easy to do the statics on, right? Things start moving around, it gets a lot more complicated. But in statics, everything's at rest. So gravity pulls down. So we do get a lot of parallel systems.
So the most part, we ignore force. Or is that, no, that's.
In the beginning, we're gonna ignore it. But then it's gonna pop into place when we get into strengths. Yep. Like, how much does that beam weigh? We don't even, they don't even give you that information, right? And that beam could be heavy. It could be steel, could have a lot of weight to it. Which would be another gravitational, right? Another force acting down, trying to rotate things. So that's what a moment is. You're gonna calculate some moments. I think they even have you sum them up, right? So do them individually and then just add them up and keep their sign straight. So signs are pretty easy with parallel systems, like so what here, I'll call it F1, F2. I don't need distances just to think about the sign of the moment. So if I said I'm going to do moments about B, what is the rotational sign of F1? About point B. Yeah, so the way I do it is in my brain, my simple brain, I attach a string to the arrow and then I let it go, right? And it goes like that around point B. And then I look at this rotation and say, oh, is that counterclockwise or clockwise? It's counterclockwise. So that moment is positive. Because counterclockwise is positive and clockwise is negative. And then what about F2? About point B. Negative. So it's very dependent on where you're at. Because if I would have said point A, everything would switch. Okay, so just be careful with that. All right, looks like you have one of those for part of your homework. So good luck, and we are done.